3. Oh wait, hold on. I should probably start on camera. It doesn't matter what camera we start on. Oh, I forgot to set up the back camera. Hold on. But I'm pretty sure we're actually live at this point. Let me check. Switch account. Switch to data science. That's not what I want. And now we're about to get DMCA claimed.
Yeah, 15 seconds.
Yeah, just
so we are live. I can see it on YouTube.
All right, we're live. Well, hold on. Just because we're live doesn't mean we have data sending to it. I have it on a timer, so it should go live regardless. If I mess up or not.
Oh, it's a different camera. I can see the back of y'all. Oh, now I see myself.
Okay, cool. That means we're having data perfectly. Hey, Colton.
Oh, hi, Colton.
All right, perfect. And in 20 seconds, you'll see yourself again, and you'll see everyone who. Well, actually, you can already see everyone who's in the room.
Well, yeah, now it's a big screen. But yeah, forget the YouTube. Just let me know whenever I can. I think I need access to share my screen, and then I can.
Can you do that for me?
Yep. Maybe not.
Oh, yeah, so it's security, it's allow participants to share a screen, and make co-hosts.
Switch.
All right, you should be good to go.
Okay.
And let's make it so we can see your beautiful face, because why not?
Yeah.
Okay.
All right.
Like, this is Zoom. Okay, I'm trying to make it so I can see you all still.
All right, you're
while I'm
good.
Presenting.
I should have told you earlier, but try to safe line the right side. And then let me know if we need to change that up.
What? Are you talking to me again?
Yeah. Don't worry about it.
Okay.
All right, before anyone asks any questions, raise your hand so we can switch mics so he can hear you. Or you know what, we could also just, that's not what I want. How did that happen? Oh gosh. Cool, whatever. I was trying to hide this.
That doesn't need to be perfect, I think.
Whatever, it works. Travis, you see what happens on the other side, so try to keep away from that side of the screen if you can.
Wait, from what side of the screen?
Right side of your screen. If you have anything there, don't worry, I'll figure it out. As I always do.
I'm confused.
Don't worry about it. You're good to go. All right.
Okay.
Hello, everyone. Welcome. Today we have Travis Hammond. He is a machine learning researcher at Johns Hopkins University. He is a former president of the Data Science Club here at Sac State. And I have strong-armed him into coming and giving a speech today. If you want, we have food at the back from Subway. We have sandwiches and cookies. Please make them disappear. It makes our budget go down, which makes accounting happy. All right, and without further ado, Travis Hammond.
Cool, thank you, Aaron. So, hi everyone. Today we're going to be talking about intelligent neural networks, or really intelligence in the context of neural networks. Before I get into anything major, I will say that a lot of what we're going to be talking about today is related to the bias and variance trade-off in machine learning. If you've heard of that, that might help you understand some of the concepts, but from here on out, we probably won't mention any of those terms in their original meaning again. But those ideas are a common theme throughout. With that, we're going to be going over
kind of how I've defined intelligence, how I think it might be useful to define it, some attempts, basic context of like attempts in that domain, and then we'll get into discussion. This entire time, I want it to be a discussion. In the beginning, I will go over a couple slides to give some context, but feel free to raise your hand, whatever Aaron has to do to get the mic to hear me. and then ask a question, because this is not so much as just take this in and learn. It's more of a exploring what this means, because every single day this week I've changed the slides, and weeks before, back and forth going between different things just because of I guess how I felt that day. So getting your input is just as valuable as me getting to show and share this stuff with you. Okay, with all that, this will be our outline. So intelligence, attempt, discussion. And again, like I said, discussion can be throughout. With that, we can talk about what is intelligence. So we don't know exactly what it is, but we have a feel for it, right? So if we can see something and we'll say, oh, that's not it. Or we'll see like a human and we're like, oh, well, they did this and that seems intelligent. But often it shifts around. So when we have things like chess, we wanted to make an AI solver for chess and it solved it. And then we're like, well, that's not intelligent. What if we solve Go? Maybe that will be intelligent. And then we solve it and we're like, no, that's not intelligence. And it kind of moves around. Now, I would argue all of those things had some varying level of intelligence, but they weren't what we were seeking in terms of having something that has high levels of intelligence. With that, intelligence is also somewhat context dependent, and it is just debatable in different things. So that's why I want to narrow our focus down to neural networks. Although intelligence as a whole is going to be a common theme, because we have to define it somehow, I want to say it is context dependent, because I'm not going to have the audacity to fully define it for all circumstances. Okay, so with that, how would we define it? Well, I think the best way to approach this is the practicality of what do we actually want and how that kind of relates to how humans generally roughly define intelligence. So with that, we basically get something that is an algorithm with the ability to handle novel tasks with limited information. And that limited information can be directly related to that task that you're going to, that novel task, or it can be indirectly related. I want to narrow our scope a little bit, because we can get into this problem that I've often found myself when I was doing this type of research, where intelligence is not like this magic sauce that solves everything. Though it kind of is, it's something we can't practically do if it's magic, right? So we have to bring it down to our like environment where we have the tools and the current understandings to try to approach it. And so with that, we're not trying to make a algorithm that can solve like every task, or solve a task that has no information for. So if you, for example, if you wanted to train a neural network and you had this intelligent algorithm that we want, that network would not be able to solve a problem where you trained it on ImageNet. Oh, actually, let me give you a better example. So you trained it on MINST, which is basically optical character recognition of digits. So 0, 1, 2, 3 to 10 or to 9. If you could do that, we then wouldn't assume you could go to ImageNet and perform 100% accurately on ImageNet just by being trained on how to recognize characters. And so that we're not saying. What we are saying is if something's directly or loosely related, but not super closely, we would want something to perform well on that. So that's kind of how we're going to define intelligence and continue to define it throughout this presentation and discussion until you guys say otherwise. So with that, we can ask also how we want to achieve this. And throughout this presentation, like, we won't get a consistent answer, and we won't have the perfect answer to make it so you guys can go make your neural networks and solve this problem or anything. But we're really going to just go brainstorm, go through my process of brainstorming that I've already written out here, and maybe get something. So next slide. So here I try to get a little more specific. And from that definition of what intelligence is, we just defined it: ability to handle novel tasks with limited information. We now can get some estimated math formula for this, where we say intelligence approximately questionably equals intelligence with respect to a training set. So D is a training set here. Aaron, can you guys see my mouse? Because that might help to. Okay. So intelligence approximately equals intelligence with respect to your training data, T, your test data, and then M, your model. And it's questionable if you need this model for intelligence to be relative to that. I'll explain it in a moment a little more for why I question that. But essentially, from our definition, we just put this into some mathematical functions where we say novelty, we want a novel task. So a novel task would mean your training data is novel compared to your test data. And so that's pretty self-explanatory. The specifics of how you would want to farther define novelty can be a little more complicated, and we won't get into. But if you had questions in the discussion or whatnot, I could try to answer that. Then that's all over. That novelty is over by the error of your model, essentially. So model given D trained on your training set, basically, and then how performant is that on your test set. So in the context of neural networks, that's really like almost like your mean squared error or like your normal loss function in a neural network. That's kind of what this is, but that's your validation or your test set. So we're not talking about training your model with this error. We're talking about validating it. And then that's times by the number of biases in your model. And from here on out, I'll say biases, and I really mean inductive biases, but they're pretty similar. So I'm just going to say biases throughout the rest of the presentation. And these biases can go from anything like if you wanted to hard code every single thing you would need to play chess, that would go under the number of biases. So like every single if statement or something like that. Now, these are all like approximations, right? No, we don't have a definite definition of how to calculate the number of biases in a model. But assumingly, if you had a model, if you had hard coded everything you would need to play chess versus having less rules, but such general rules, so that you don't need as many biases, as many hard coded like if statements per se, that would be the number of biases. That would be the number of things like that. So essentially, with that all kind of explained, you would have novelty divided by error and the number of biases. So as novelty increases, your intelligence would increase if everything else is constant. And then as error decreases, intelligence would increase.
It's 3
and
o'clock.
Say that again? Oh, okay. And the number of biases, as that decreases, intelligence would increase, and as that increases, intelligence would decrease. So this is a little confusing. I'll explain it a little more, but does anyone have any questions or want to say this is completely false? Because I thought that yesterday. Yeah. Yeah, go ahead.
Yeah, go ahead.
Or not.
Or not. Go ahead.
Go.
Can this equation also be used to calculate the intelligence of both the machine and the human who has either a high or low IQ?
Okay,
I'm actually really glad you asked this. So I don't know if I explained this a little more in detail in like a later slide, but this is what I love about this, because IQ tests and things like that, and comparing intelligence is like such a questionable thing. Like we kind of accept it, but kind of like we all are like, it's not necessarily the best thing. And this equation kind of explains why that would be problematic, comparing the intelligence of the machine versus a human. And that's because when you're defining intelligence, it's that scalar value that gets outputted by this equation, which again, we don't actually have like the ability to compute this, but in this theoretical realm, why is my face? Okay. In this theoretical realm we're in defining this, the intelligence is with respect to that training set. And so a human, per se, training set would essentially be all your life experience since you were born. And so that's like
obviously unique to every single human, and also going to be completely different to a machine. Another thing with that is that training sets can be like, if you're doing an IQ test, they give you a couple examples and then you're supposed to proceed. That would be constant, but your whole life prior is not. It's different to every single person. So that's why we approximately say we can compare them maybe, but it's not going to give you the best comparison. And then also normally on an IQ test or whatnot, your test set would be the same. But so we could ask the machine the same questions as a human. But again, that training set's different. And then the model, this is questionable. Model it may or may not impact like if you can compare the the intelligence of a system, but you can think of that as like for a human, that would be like the genetics and whatever other factors had play in the development of your brain, essentially. And yeah, so it basically, to shorthand answer your question, that is a very hard task to do, but we can approximate it by trying to do things like giving the neural network a similar training set as a human, or at least trying to give it some context that we humans already have, and try to put it on a level playing field. At the end of the day, if it's smarter than a human in every way, who cares if it's intelligent? So this will be a theme we'll see as we're talking about intelligence, but intelligence isn't always what we want. We want really something that just performs better than us in every way. And so, or at least on par. And so that's kind of what we'll see, a trade-off between intelligence and actually we just want to do good. And who cares if we don't have intelligence? Okay, hopefully that answers your question. Any other questions before I move on? Or ideas or
anything that are spurring in your mind from this? Else I'll go on. Okay. So the next slide here, we get some insights from this.
So assuming this formula is somewhat correct, at least, we can see a couple things from this. So first off, large amounts of training data do not impact directly intelligence. And so this is kind of important, because we think of things like ChatGPT trained on like the whole internet, and we say, well, it was trained on the whole internet, so it must not be intelligent because like it literally knows everything. Well, that may be true that it's not necessarily intelligent because of it, or at least not highly intelligent. It's not because it was trained on a large amount of data. It's because it doesn't perform well if you were to give it something it's never seen, and have high novelty. So that equation at the top, that formula, or that function, excuse me, at the top here, if you have the whole internet as your D, as your training set, and then your test set is something that's never existed on the internet before, and never been seen before, then you're going to have high novelty, and ChatGPT is going to perform badly on this. And that's where you would get like ChatGPT has a low level of intelligence. So the problem with ChatGPT, and more so with training with large amounts of data, is it's inherent that if you train with a lot of data, you likely will have low novelty because you've seen everything, or at least some rough amount of everything, that you're just going to have less novelty. So you may perform well, but because you have less novelty, it doesn't really matter as much in terms of intelligence. Okay, so from there, I kind of just explained a couple other points below, but basically more data can reduce novelty. So that correlation, the fact that you would have more overlap, because if I show you a bunch of numbers, as in this minced example here, if I show you every single approximate, like almost every way you can write a zero, like there's not that many different ways you can write a zero. Like maybe it's a little taller, a little shorter, a little more to the left to the photo or whatnot. But ultimately, if I show you enough of them and then ask you, is this a zero or not? You should perform pretty well, because there's just not much novelty there. There's nothing new. And so that overlap can reduce novelty. And again, as I was talking about in the previous slide, that's not always a problem. Sometimes we want to reduce novelty. We may still want to have an intelligent algorithm backing our model, and backing what is making these predictions. But the practical trade-off is that if we can get better performance with more information, with more data, then we might as well do it. And that's kind of what foundation models, ChatGPT, and the like have done. Also, optimal biases are needed over lots of data. So this essentially is talking about, we can use a lot of data, but if we had really good biases that allow the neural network to generalize more powerfully, that's going to be better than a lot of data. So the example I like here is thinking of feed-forward networks, so just a normal dense layer where everything is connected, versus a convolutional neural network where essentially we have these biases, these priors in the network, in that architecture, that allow us to learn image recognition tasks easier. And that's because we have a bias that in the architecture that lets us understand things like that, or lets the neural network understand things easier in that sense. And of course, yeah, sorry. Okay, so that's basically for that slide. The last thing at the very bottom is many biases can reduce intelligence. This goes back to what I previously mentioned. If you hard-coded everything you needed to play chess, then you're obviously not really, that algorithm itself is not going to be intelligent because you hard-coded everything. And so it should penalize intelligence for that. All right, any questions on this before I go to the next slide?
Okay, I'll move on.
We have one.
Wait. Okay, so how can we achieve high intelligence? So again,
we have that formula above here. Well, we really, from looking at the formula, if we minimize error, and if we minimize the number of biases while maintaining novelty, then that's basically what we need to do. Like if we could optimize on that, we would get intelligence. Now we're not able to actually directly optimize on this formula. If you were thinking that I've tried it and practically it doesn't, or theoretically it doesn't work, because if you train on intelligence, if that's your loss function, then inevitably, I can't say the word, no matter what, your test set is going to become part of your training set. And then that will throw off your novelty, which then throws off your intelligence. And then you can't really do much from that. So unless you had a perfect approximation of novelty so that you could backwards pass through novelty and everything, which I doubt would be possible. So long story short, we can't do that. And so what we find is that practically we want to create a model and a training architecture that has highly effective biases. So I probably already said this in the last two slides. Like this is really where all this is going, is that the way we get high intelligence, improve the intelligence of neural networks, is improving the biases, the architecture, the training process in the neural network. It is not by necessarily giving it just more data. Giving it specific kind of data could have some impact. And so basically we want to prioritize that. We want to focus on finding the best way to make our architectures more inclined for generalizations that we find in humans and the like. And yeah, so we want the model training set and the test set will probably hold constant. So actually explain this better in the next slide. When we're trying to like optimize for intelligence, we will hold the training set and the test set constant, right? We're not going to change this because that would be cheating this problem. Like we really like if we have an example, an out of domain example for the test set, and then we have a good training set, there's no reason to change that from now on. So then the only thing left to really vary in this formula is the model, how we make that model, which goes into the biases. And so essentially what we want to mess with is the biases. We want to have powerful biases, and more specifically, we want these biases to be generalizable, yet just as effective as having like a bunch of biases. So if we could have two biases that make it easier to recognize, like, the zero, like to recognize back to the optical character recognition of those digits. If we want to recognize zero, if we have two rules that help us recognize zero versus like 20, that it's going to be better to have two rules that do just as effective work, allow the model to perform just as well, but with only those two rules. And so that's kind of the variable for intelligence. And then going back of, well, intelligence isn't necessarily what we want at the end of the day. We want performance. And to do that, that's where we would hold the test data constant, and we'd be varying biases and the training set. So maybe we found some good biases for the network. Now we want to go into just increasing the training set, optimizing the training set, changing it so that we actually reduce novelty, so that we just make it easier to perform better and have a less error. So yeah, any questions on this now? I'm going to kind of transition in the next slide.
Any questions on the last two slides I've covered?
I think Mosh has a question.
Can you go to the last slide, please?
The previous slide?
Yeah. To achieve high intelligence, if you're going to make an AI machine do that, can you also make a human also achieve high intelligence and try to increase his or her IQ in the process?
So actually, that's a great question. I was today watching a YouTube video that was explaining some like first principles thinking and some other things like systems thinking and such. and they were talking about in IQ and stuff for a snippet in the video, and that relates to this because essentially humans, like, there's an argument for that intelligence in a basically from a certain age does not change through the rest of your life. So there's like evidence basically that you don't learn intelligence, you're basically, people would say like you're born with it, or at least from an early age that's constant and then you can't change it. I think to some degree, because there is research showing that that is true, but there is early stages in your life where your brain is more able to learn the core, like it before, basically, like I like to think put this in, because we don't really understand the human brain. So I'm just going to go back to neural networks and hope that's a good enough proxy, artificial neural networks, I mean, that as we're training on a data set, usually we start to converge on something. And once we've converged on a data set, usually it's harder to shift now from that training set to something new. So in the early stages, when you're younger, hypothetically, like in this, I would maybe say this applies to humans. As you're learning in the early stages, especially in your earlier years, I know there's research showing that you will learn faster and you'll learn things and be able to learn those things easier, quicker, and more adaptive than like when you're older. And so from there, all that to say, to answer your question, there are ways where we could hypothetically, when you're young, we could make you like super intelligent. And there's actually, I forget the guy's name, that there's like, there's this guy that I believe his parents like basically indoctrinated him to be super intelligent, and like he was super intelligent. Like now, like there with limitations, like you focus, like the human brain usually only has so much processing power. I think it's like 19 billion neocortex neurons you have, something like that. And so and that doesn't, like, that varies like by a couple billion, I think it's billion, it might be million actually. It varies between humans. But to answer this question of high achieving, we would probably have to have a special way of teaching children to increase their intelligence. And that would be at some cost probably to something else like social interactions or something. Because if you're focusing on one thing, that means you're not focusing on another thing, which might actually be core to how you do stuff in the real world when you adult. And also, we don't have modern technology to make your brain, like grow your brain cells and make it so that you can have many more brain cells. And I honestly don't know how much that would help. So to answer your question, no, basically.
You can't even do the same with someone with the conditions, ADHD or somebody who has autism spectrum disorder.
I don't know. I definitely am
not an expert in anything in the neurosciences. I only know the bare minimum to try to do AI research. So I would not have that answer.
But you would also not be thinking about implementing anything into machines or humans, such as software or physical injection with some.
Yeah, I mean, I'm sure at some point it possibly could be.
Like it could be possible to increase the number of neurons and things in your brain to help restructure your brain to do different things like that. But from this research I'm talking about here, we're really talking about neural networks. And in that context, neural networks start from a blank slate. They have no biases, well, depending on the architecture, but basically starting from scratch, there's not much that a neural network is like going to automatically do. It's all randomized for the most part. And so we're starting from such a like bare minimum that even a human that's like a baby that just is born in the real world for just a couple months will already begin to have architectures just based on like the DNA and how brain cells are made and whatnot, to have all these biases for the real world. And neural networks, when we make them, do not have that. And so our goal here is to start approaching the human side by making those biases that our brains have and putting that into a machine, putting it into a algorithm to allow us to do that. So humans already kind of have the problem solved. It's really like, how can we translate what humans have into these artificial neural networks? All right, with that, because I do want to make sure we have time for discussion, I'm going to move to the next slide. And okay, My slides are off. Already talked about that slide. Okay, so now I'm going to talk about neural networks for a second. This was really all of our talk was supposed to be focused on this, and we haven't talked too much about their behavior, how they learn, their limitations quite yet. So neural networks directly do not have much intelligence. If you ask me why I know this, it's because if you train any model and then give it some somewhat out of domain example, like if you trained on mince, on that example of that I had previously over here of those digits, and then next thing you know, I write this on an actual piece of paper and ask the machine, can you do this without the black background or with more noise in it? It will fail. And so that's why I would say neural networks do not have much intelligence. They only, from my understanding, they only really optimally memorize connections between low-level features in the inputs to relate them to the output that you're training the model on. The optimal goal, the loss function that you give the model, in the limited resources in the network, like the number of parameters, forces prioritizations for generalizations and memorizing low-level features. And by low-level features, I mean really easy to learn, easy to model. There's not a lot of variance. They're consistent across different examples with the same expected output or similar expected output. And with those limitations of the network that produce somewhat of these generalizations and memorizing low-level features, those memorizing features occur from basically the different training sets. So in the training set we have, you have different examples, and it will try to memorize the low-level features that basically cover all of those examples. You have 10 different numbers, and you're feeding, and some combination of those 10 different numbers equals dog or cat or something like that. If the neural network found that at the very start, that first number, if it was a 1, it was a dog, and if that first number was a 0, it was a cat, it would ignore all the rest and it would just focus on that, because that is the most generalized thing it can find in the training set that allows it to differentiate between the two random inputs we're talking about. Why is this a problem? Well, the problem here is that a neural network, well, first off, it's a good thing, right? Where the model is generalizing because of these limited resources. But the problem with this is this memorizing of low-level features can lead to overfitting and not allow the model to go out of the training set and into a test set or out of domain test set. And so that's problematic. This memorizing of low-level features, and by memorizing, to be clear, it's really, I'm talking about like the model is learning specific things that it's hard coding into its weights, like to try to explain that. It's learning these specific things to memorize so that when it sees a certain combination of something, it will then conclude this output, based on that input. And so that's problematic because it doesn't, as we've already just talked about, it doesn't generalize. This doesn't generalize enough. And really, this comes to a fundamental problem with neural networks, that if they're just memorizing these low-level features that it can share, there's nothing we can really do from this current perspective to increase the intelligence in the neural network. Because all it can do is memorize. If it has more resources and more data, it might do a little better, but essentially you're just doing a some statistics of which variables have the most impact in determining this, and I'm going to memorize that, and that memorizing that might not help you in the future, because that memorizing of that specific low-level feature might not be the only feature that determines if it's this type of output or not. So with that, how does this change? How do we get out of this problem with neural networks? So we do this by having those inductive biases. So I've been talking about this a lot. But practically, what's that look like? Well, a convolutional neural network is one example I've given before, and that works not because it does anything changing neural networks inherently in the sense that we're training with limited resources and with an optimal goal, a loss function. What it does is it makes the low-level features that the neural network is memorizing, hard coding into its parameters. Those low-level features are intrinsically going to generalize more powerfully when we're using a convolutional neural network in the context of images. because of how convolutional networks are related to viewing images. They have assumptions like if one object is up here in an image, it's the same as being down here. And so those assumptions allow the network to perform better because those low-level features are inherently going to generalize more powerfully. So with that, how do we do this? How do we do this farther? How do we take this farther? Well, we want to improve the neural network. There's two routes. We want to improve the neural network so that the low-level features generalize well. So that's something that's not, that's something that we've already are solved to some degree with CNNs and even better, transformers. Transformers, which I think I have a photo in a later slide, are really a powerful generalizing mechanism that allow us to just improve the generalization and memorization of low-level features. The next thing is less tested, we have less research in, is we want to train an architecture and model architecture to have extreme generalization capabilities. And this is a questionable way, like this is a hard thing to figure out how to do this, how to really structure the architecture to, it's kind of goes into like, well, our brain's so complex. We have different parts of our brain doing different things. There's all this recurrence in our brain, things going in themselves. It's just a complicated thing. So how can we even begin to understand how to architect a model to handle the things that our brains handle? And so some things into that would go into, we want a architecture that can handle varying input sizes, and transformers help with that, because we don't want to be limited to the size of an image. If we don't want to resize an image, we want to just be able to understand everything we are given. So making an architecture that can handle varying sizes, varying output sizes, and also have some ability to have higher level ideas and handle those better. That's a real struggle of neural networks that we have not figured out, is how do we allow the neural network to have a deeper understanding without training on the entire network, internet, I mean, for a really long time on a really big model. So those are the two routes. With that, we can move into attempts that kind of just context of different ways, algorithms we have for current. But before that, does anyone have questions on the limitations of neural networks? Because this is probably the more practical thing we'll be talking about, because a lot of this is theoretics and like AGI stuff that doesn't necessarily matter when you're doing a data science position. But having a practical understanding of like neural networks are limited by the intrinsic ways like of how the neural network trains with gradient descent and all those types of things may help you understand what you're doing on a day-to-day if you get a data science.
Good.
Do you limit the neural network so that the computer doesn't like become self-aware and try to be independent from human control?
Well, nothing I'm messing with has the capability to achieve anything near that. And I would believe that if we began to see that, there would be more precautions I would be taking if I was achieving anything close to that. I would expect the beginnings of a neural network to be that is increasing intelligence to just be able to handle harder cases. Like if you are learning the MIMPS data set that I talked about previously with recognizing digits, if you could learn that and then perform pretty accurately on like the fashion data set, which I think I didn't super highlight, this fashion data set here, if you could learn how to recognize these digits and then carry that over to recognizing a fashion data set, then I'd be like, okay, we've actually started to solve something here. Maybe we need to take more precautions. But until something like that occurs, I am not taking those precautions right now.
We don't end up having a similar story to what happened with Skynet, for example.
Yes, we definitely do not want Skynet to occur. I think the failure they did there was thinking that if they put an untested AI, I believe it was untested, in control of a bunch of nuclear weapons, that it was going to go well. So yes, we would definitely be testing and making sure our AIs are performant before anything close to that would occur. And hopefully.
Question.
Well, let's not forget that includes the manufacturing of machines known as cyborg terminators.
Yeah, we would hopefully not do that.
Yeah, we would hopefully not.
So in terms, so it sounds like you're talking about like proclivity to like learn and then kind of that's limited by the ability to recognize sort of how much variation there is to things.
Yeah, essentially, yeah.
Essentially, yeah.
Is there, does something like a bias weight that more? Like, which of these variables would you think weights that more heavily? The proclivity, the ability to learn and recognize new things. Is it a bias? Do we have to have better biases? Would more biases make a bigger model or shrink a model?
Okay, yeah. Great question. So essentially, a training set and bias gets really messy. I like to think in the human context, if you've done something a lot, practiced something a lot, it starts to become more of a bias. It's a like an intrinsic thing in your brain basically. And it's less of like just a training set, because a training there's in a human context there's a lot of varying, like, okay, I've memorized a couple things and now I'm going to be able to do this, versus it's like deeply ingrained in how I do stuff. There's so many different levels. In the context of a neural network, there is some questionability of what goes into when you start pre-training models. If you pre-train a model, is that start to become a bias, or is that still your training set? And so does that kind of start to answer your question?
I think so. It sounds like
Okay.
we're still figuring it out.
Yeah, no, we're definitely still figuring this out. This is a all over the place type of thing. I really think it's a combination of special learning scenarios that you would be putting a neural network in, teaching them, because what I found from actual hands-on research in this, that quite simply, neural networks do not want to converge on intelligence, like intelligent behavior. It's just not going to happen easily. And so what often you have to do is you have to kind of like hack the learning by giving it like an easier task, or teaching it fundamentals before you start doing something more complex. And to go on that even more, we don't know the biases. We really like the best bias I think we'll achieve, and hopefully we get something a little better, is transformers. Transformers are so generalized, but so perfectly structured to learn so many different things, but learn them optimally, that's like the best bias we can give it. Learning anything more starts to become a part where we need to do something like self-supervised learning over the whole internet. And then we can maybe extract those biases, extract those learnings. But it's such a hard task to really get. So, excuse me. So yeah, it starts to break down when you bring up those topics as formula. But I think it'll be a between both. I think it'll be training set matters, and specifically the architecture of your training. So not so much like if you're trying to solve MINST, you're not going like, we're not changing MINST, but we might change how we're feeding in MINST. Are we feeding it in as a group of images? Are we giving it a single pixel? Like different things like that. That might change.
So I'm going to go to the next slide. And I like this part because now we're kind of getting into the attempts of not so much how we actually can perceive from this.
That is a unsolved thing that I would encourage you to research and try if you're interested. But currently, what do we have? Well, we have low intelligent algorithms, and we have less than higher or high intelligent algorithms, but we do have things that have a varying spectrum on this intelligent axis here. And the very beginning is k-means, and I absolutely love k-means as an example for intelligence. To simply explain what k-means does is that it looks at many different embeddings, many different vectors or list of numbers between a data set, and it will just unsupervised, without having a label, cluster them together if you tell it how many clusters.
And so if you take
let me think of a good example. If you were to take everyone's math score in a class, on some exam in math, and you were to say, I want, I don't know, 4 clusters, and you took everyone's score and you clustered it to 4 different clusters, those clusters would be, and obviously you would have to give it some extra information. So we could give it like how many hours you studied for the exam. Do you like this class? How interested you are? And we give it all these different factors. And then we would cluster it based on those factors and ask it for like 4 different groups. And we might find after the fact that those 4 different groups that it clustered are going to be correlated to your actual exam score, to some, like maybe to your letter grade or something. It's not a perfect thing, and that's why it's on that very minimum of low intelligence, but it's a perfect baseline because the concept helps us start to understand what are we even trying to do with intelligence. What we're trying to do is we have a bunch of numbers and we're trying to correlate them and figure out how they relate to each other. So k-means, the bias in k-means is that it's looking at the means. It uses the means of each data point in the values in the embedding to decide where it should be clustered, which group it should be in. If we had k and then not means but something else, k image, and we have an image model trained on outputting vectors, embeddings that are going to be close in Euclidean distance to each other, that would start to get into the lower intelligent algorithms. But essentially what k means is the bare minimum. It's just, here's one simple bias, just one simple rule. Look at the means. If they're close in Euclidean space, then they're going to be the same. If we mean that group together and they're close, then they're going to be the same. And so I really like that because it will carry out in all these problems, everything becomes a k-means problem. And going above the normal k-means, we get into just traditional neural networks. And they are doing that same thing. They're trying to learn k dash and then whatever your specific training set is, and it will learn what's the best way to cluster your training set to that output that you want. And what it really is doing is memorizing and estimating what those embeddings and how they correlate to each other. Now, to start getting a little higher on this spectrum, we introduce ideas that are more advanced ideas in neural networks. We start getting into things like meta-learning. Meta-learning, it has so many different definitions. I really just think of it as a +1 on the difficulty and what you're asking a network to do. And so it's not, so one example is if you train a neural network on, if you give it a group of examples of dogs or cats or something, and you label those cats and dogs, you give them like 10 examples of each, 10 dogs, 10 cats, and you're telling the network the labels to them, and then you give it one extra image and you say, is this a cat or dog? That's kind of a rough example of meta-learning. What would arguably not be meta-learning, but I classify in this same category, is just more difficult task. If you are making a classifier and you want to classify dogs or cats, that's a pretty low level task you're asking the network to do. If you ask the network to, instead of just classifying cat or dog, do segmentation of the image so that it outlines the entire cat and it outlines the entire dog, now the network's having to learn something a little deeper about what's a dog, what's a cat. Because now it has to learn how to label the background as not a cat, not a dog. And now it has to label the cat as a cat or a dog and know every single bit that connects to that cat or dog. So now it has to learn something deeper. And then we go even farther with instance segmentation, where the network no longer just segments the image to dog or cat, but each unique dog in the image and unique cat in the image must also be labeled unique. So now it's learning the difference between dogs and cats. So it's not just a single dog, it's learning what parts are in the dog and how to represent a single dog. And so from all that, this meta, like the step above of what a normal task would be of just classifying, we start making the neural network have to learn deeper understandings to perform this task. It doesn't necessarily improve the generalization like to an extreme amount, but when you're learning these harder tasks, you start learning deeper. Concepts. The network starts learning deeper concepts that allow it to generalize a little better than the previous traditional, let's just train a classifier neural network. And then the last one, which is for higher intelligence, is a little questionable, is self-supervised learning. The premise here for why it would be higher in the spectrum is that if we're training on in a self-supervised method, so supervised learning basically is, I can give a natural language example. If I say, hello, how are you? And I give that to the network, and then at the very end, I remove the you, so or hello, how are you? Remove the you, and then I would ask the network, predict what comes next, and then it would say, well, you. And then if you train it on the entire internet, you would get ChatGPT. But essentially, that's self-supervised learning, and you're not giving it a specific task. All you're doing is predict the next token. Now, when we translate that to other tasks and fine tune, all of that understanding to do that fundamental predict next token, the network had to understand so many different things that it starts being able to generalize and connect dots of different things that we wouldn't easily have connected without using a large amount of data. So this kind of goes into that previous question of, is it your training data or your biases? And well, to some degree, if we're just using a lot of training data and self-supervised learning, it does help probably in intelligence. Again, these formulas and these things are estimations of where they fall along. But I would argue that self-supervised learning is a little more up there. All right, last thing for this slide is high intelligence. That's what we want, right? That's really the whole point of everything. Well, I have no answer for you of the exact solution. But as I was mentioning of k-means, I love k-means because k-means, in essence, is going to also, as it is the lowest, it's going to be the highest, in that k-means, not the means part, but the k, where basically we're comparing embeddings and finding the correlations between everything. That is the task we're trying to do. That is what we want to do. And so if we had a biased k-means for image recognition, if all those embeddings, we could understand them in the light of everything we would need to understand to recognize images, that would be the biased k-means. Now, k-means is really breaks down because really what all I'm talking about is, well, just make a neural network that outputs embeddings, train it on the entire internet of images. Now it outputs embeddings of images, and then use normal k-means. That's basically what I mean by biased k-means. Because assumingly, if you train a network to output images in a Euclidean space, then similar images would be closer to each other, and etc. So then you could just run it on normal k-means. So not really an answer here, but that might be how we can get high intelligence. That type of thinking of how can we best correlate data. So I'm actually going to move the next slide because that's where I talk about this farther. We essentially, to attempt this from all of what we just talked about, we want to create a model and training architecture with highly effective biases. So we stated basically this previously. And we want to increase the ability of the model to use all of its training data in an optimal generalizable manner, having an out-of-domain test, right? So how do we do this? Amount of data does not matter so long as we have novelty. So we've already kind of said that, right? We also have the model, and we can predict. So if we have the data, doesn't matter how much, we correlate all that data optimally, and then we put that in a way where we can model and predict, then we would solve this problem. The real thing comes down to optimally combining. And so just to speed up a little bit, I'll go to the next slide. And I kind of put this is I didn't get fully into this, but essentially we want to solve, like, the model we want is this model called C. And C has input and training data, the current input, and then all your training data. And essentially what you want the model to do is best correlate all the training data with the input, correlate everything within the input with itself within the input, and all of that together. You want to best correlate that, and then you can get a good output. And to some degree, that's what a transformer does. I don't have time to super explain it, but a transformer allows you to correlate your input well with the other segments in your input, and produce good results. Okay, I want to move forward so that we can kind of get into discussion. I know we don't have much more time. Jokingly, what's the solution to this? Well, I don't know. So if you've ever heard what's the answer to the universe, everything, etc., it's 42.
Computer scientists
I swear a computer scientist must have put this in deliberately, because 42, if you use alphabetic numbering, it goes to dB. And if you could translate dB, if you treat that as hex and then go to the ASCII extended table, you get U hat. and you had, assumingly, would stand for the universe approximation model. And so if we had that, we would have all of what we need, because if we have all the knowledge of the whole universe, we no longer need intelligence. And I think with that, I think we should just end, because who needs?
Any questions?
Thank you.
Well, yeah, no. So, okay. I mean, just on that last point, I guess I was reading something about how there's a linkage between like intelligence and downsampling of information, that when you are learning something, you're not learning all the bits that might describe what you're learning, that oftentimes it's being like, what do you call it, like optimized, but that then in order to have a universal model, wouldn't then we need to be sure that we have a finite universe?
Yeah, no, it definitely breaks down. I was more so joking, but I think
if you had some approximation of everything, so not maybe we have the perfect mathematical equations or physics for everything in the universe, but if we had some decent rough estimation, then we would not need intelligence, because we would have trained on every data point we ever needed. Yeah, so it definitely wouldn't perform maybe 100% accurately, but it would perform maybe 90%. And in all the human domain, it would perform always better than a human.
Yeah, any other questions on K-means, neural networks?
We're gonna let, yeah.
And then the person in the back after.
He sees you.
But yeah, let's just hope that we have a test subject where we try to make a person with some low IQ become smarter, but not to the point where they end up trying to,
So
take
no
control of
Robocops.
Yeah.
You were saying?
Yes.
It's like the Lawnmower Man, the movie.
Mosh, we're a little limited on time, so let's just try and stay. I think someone in the back had a question.
Okay, I got you.
So when you said that for a neural network, you're analyzing, you were have to first train it or teach it the basics. What do you mean with the basics? Like, is it like some kind of logic, or what is it?
Good question. So obviously,
Good question. So obviously, as I have not solved this, I don't have a full answer for you. But what I mean varies to the problem you're trying to solve. So if we're trying to like approach making a model that is as good as a human in everything a human would do, you would want to teach it core things to being like a human. So example, like priors for humans. So like I don't really have them all in my memory, but if we have object recognition, right? Like we understand this idea of objects very young. I think it's like when you're less than 1 year old, you understand like a certain number of things intrinsically. And a neural network is starting from scratch, right? It doesn't have this in, I like to use the example that like humans are endowed with this special knowledge in our genetics and how our brains work. We have like the neocortex is more general, but we have a lot of things in our brain that are very specifically made. And when we get into the world of neural networks, there's none of that, aside what we're doing. And if we're not doing it, then that means it has to learn it. And so if we're having to teach the network to think step by step, for example, then we might want to have a training set that in the beginning, we start showing it, hey, it's actually better if you output something you think and then read it in again and think on it more. Like if we can, this isn't a perfect example, but if that type of idea of, oh, if we want the network to be able to do that, we should teach it in the beginning. This is a good way to solve problems. Because as I mentioned previously, optimizing a neural network on intelligence, and you can't do it directly, but if you find a way to do it indirectly, it does not work well because intelligence is such a hard thing to optimize on. It's such a hard thing to optimize on because it's such a complex idea that everything before it is easier to converge on. It's better to converge on some local minimum than to find that optimal result of intelligence. And also, intelligence isn't always the best thing a model can do optimally. Like it might perform worse on your training set if it has intelligence. And so the idea of adjusting your training set would be teaching it to learn tasks that basically start the neural network, like jumpstart the neural network to understand these higher ideas, so that it's already in an area. So when you start training on an actual training set, it's like, oh, I already understand these high level concepts that I've been pre-trained on for thinking through my steps of my thought process, or looking at examples before I do an output, different things like that. I have no perfect example, but training these low level ideas that are high level ideas, but training them in the network to put these into the weights before you start training on a data set might be useful. So yeah, I don't have a perfect answer for that, but in the example of like ChatGPT, like they trained it on the whole internet for self-supervised learning. It didn't automatically start talking to every human politely and started helping them. You know, that was through an additional fine tuning they did. And so that kind of goes into, okay, if we want to teach it high level concepts, we'll train it before, and then on these high level concepts, converge it on that, and then transition to something else that we want.
And arguably that does not solve intelligence. Like, I think I have the slide about hacking intelligence here.
It's very problematic that if you use self-supervised learning and you train on the entire internet, and then you output those embeddings, and those embeddings will reduce the amount of novelty you have between a test set and a training set. I have probably limited time to actually explain this, but essentially you wouldn't necessarily, per my definition, and this is partly why I think my definition might not be fully correct, is that self-supervised learning might be the best way to do it, and you might not actually get good high levels of intelligence out of it. So yeah. Any last questions before I think we're...
If anyone doesn't have one, I have one, but does anyone have... is it a relevant thing? Well, does anyone else have something?
Yeah. By the way, did you make a machine, by the way, here at Sexton? I remember you had something that you made here, but then which someone else also took over when you left?
I think Aaron and Michael would be in charge of that.
Yeah, we can talk about that if you like later, Marsh. But
you talked about how this machine or whatever was Travis's baby, but since you were gone, someone had to take
we might
over.
have to reset it. Yeah, unfortunately. But
we will be resetting it.
I'll have to talk to Hannah about that. But in any case, so I guess as our last question, I was listening. I don't know if you listened to the most recent conversation between Lex Friedman and Joshua Bach, but there was
probably have.
There was a really interesting question that came up, which is without getting into the whole reasoning behind it, will hyper-intelligence, an intelligence we design that is superior to our own, lead to a higher state of additional suffering? Is that something you're concerned about? Are you thinking about that?
So additional suffering, and so I think this question is I just recently listened to. Oh my gosh, I'm forgetting his name.
But never mind. But basically, I think the best way to answer this is that we are at such low levels of where we're at. Like, we are on that lower intelligence. Like, we're not close to humans at all, that we can't even begin to understand how much of an impact everything will have, and the dangers associated with that. Like, we're not close to having something like Skynet. And if someone wanted to have Skynet right now, it would definitely horribly go wrong, because we don't have things that are able to do that properly. And so essentially, I would say there is much consideration in what we're doing and what people are doing in this type of research. But I think intrinsically, if anything is the safest route of achieving an AGI or a super intelligence, it's going to be actually having intelligence in the structure. And we may not fully understand intelligence right now, but more as we can improve our understanding of intelligence, and the more we can put that into our algorithms, I think the better that will be, the safer a machine will be, because it will have a better structure to understand the world with the data and information we give it. Yeah, I think that doesn't fully answer it, but I'll leave it there.
I'll take it. It's a hard question.
Yeah.
I don't think.
No, there's definitely impacts
No,
that it will have. Like, I think
it will have. Like, I think that the next 5 to 20 years will be completely different than probably any of us were thinking a year ago. Because of the advent of ChatGPT, large language models, different things. We have now foundational models that work in many different domains, and they 2 times speed your development. At some point, we'll have semi-autonomous agents that can help you do your work. You would likely have like I see us having a 3 times increase in productivity in the next 10 years for early adopters, and that's crazy. And that's not even intelligence. Like, as I've defined it, like, I really don't even think that would be a high level of intelligence in any of those systems, but we'd be able to do it. And so with that, like, job loss, I think that would definitely be a real thing. The chaotics in our economics of what's it look like when everyone can do 3 times more work, or a group of people that have invented these large language models that cost like hundreds of millions of dollars to do. What happens if they start taking sole advantage of this type of structure? Like, who knows? So there is a lot, even if we don't have ASI or AGI yet, there is much to still consider in economic risk.
No, I don't mean to extend it, but I meant like for the experience of the model itself. Yeah.
Wait, can you explain that?
So,
Wait, can
just that a model that is highly intelligent might have a larger range of emotions, assuming we have a general intelligence that has emotions, and so if it has these extremes or experiences something at a larger scale than we do, that it might suffer more extremely than we do.
Okay. Yeah, I think I'm remembering the podcast now.
Yeah, but that's a whole other. I don't know if we have a bunch of time to get into it.
All right, last question, Drew.
Yeah.
For somebody on the outside who wants to get up to speed on current conversations happening around AI, are there sources, podcasts, books, speakers, that kind of thing that you would personally suggest? Like, where do you get your news and information?
Yeah, so definitely the Lex Friedman podcast. His early
episodes are more focused. Like, it was literally called, I think, the Artificial Intelligence Podcast, up to a certain point. And so those are extremely valuable for getting up to speed on more of the talk about it. If you're wanting to get into the research, I think the best way to do that would, in addition to listening to that podcast, there's a couple other YouTubers. I really just let me just pull up. Lex Friedman would be my best recommendation. There's also another YouTuber called Machine Learning Street Talk, which is really good in getting into all the theoretical ideas and some of the applied, way better than I've presented to you all. They break it down into the different actual groups in machine learning and intelligence, the different ways we can try to achieve. I didn't mention any of these buzzwords, but there's symbolic learning, connectionists, different types of hybrids, different ideas that we have to achieve this. And I've really just knocked it all down to, well, we'll call it the bias. So
definitely Lex Friedman podcast.
All right. With that, we have run out of time. I'm gonna
Thank you, though, Travis.
Yeah, thanks.
Appreciate you taking time out of your busy schedule. So if we could get a round of applause for our speaker.
All the volume went out as soon as you guys started talking.
That's on me. Either way, I gotta quickly throw up the QR code. If everyone can go on the Zoom real quick, or not the Zoom, the Discord, and sign in with the link I posted 10 minutes ago or something, so that, again, we can get reimbursement for food. That'd be great. Again, thank you for everyone who came out. He disappeared. This was Travis Hammond, a previous president of the club and researcher at Johns Hopkins University. Thank you, Travis.
Applied Physics Laboratory. Just it's not actually the JHU, though I do go to JHU.
Oh, cool. Either way, thank you for coming. Thank you, everyone, for coming out. If we still have sandwiches at the back, we need to get rid of them, so please take a few to go. Again, thank you for coming. Look to your left, look to your right, introduce your name, and something cool you've learned this week. Yeah. Woo! All right. Bye, everyone.
We'll adjourn.
Thank you all. See you.
Thanks again, Travis.
Bye.
We gotta talk soon, man. He can hear me.
Bye-bye. Oh, he's gone.
Yeah.
Oh.
Well, yeah,
Bye.
what happened to?
Real quick, sorry, before everyone goes, so people have mentioned wanting a space where we can just gather outside for meetings. I don't know if you guys have heard of the Carlson Center, but it's pretty empty these days, relatively speaking. And you might, if you just wander through, find me there. So it's a pretty easy space to just hang out. So if you are looking for a space to kick back, it's got a lot of easy chairs and all that. So
Where's the Carlson
check it.
Center?
It's in the library. When you walk in, it's immediately on your right, down the long hallway. It's first floor.
Oh, there's an event thing.
Yeah, well, no, they do have events, and some of the events are related to like tech and stuff.
Yeah.
So definitely check that out. But otherwise, it's just open from like 8 to 5.
Oh.
Yeah, and they have a whiteboard, smart board you can use. You can have meetings in there. So anyway, just wanted to get that out there. Thanks again, guys.
That's by the Innovation Center, right?
By the where now?
It's in the library, first floor.
I think it is the Innovation Center.
Yeah,
So that's,
Any good papers?
Yeah.
Will you then interested in
No.
this have implications on this?
We started that's why I could try and get the stuff recorded.
Exactly. No, I took a note to just go down.
Yes.
It sounded like 2 minutes ago. Because it's saying.
No, I've got time.
He also has
Aaron's got a,
posted. Oh, please don't crash on me. I still need you for 2 more minutes. So he also, in learning resources, he's just posted a few. But if you look through there and you search for his name, he's posted a few papers throughout his time here. So you
What's
can also
his name?
Yeah.
Travis.
So he's not president.
Yes.
It depends on
It was a
the-
big
on
whole
the
joke how
framework
his name
we're
was
speaking.
president for the longest time, even after he was gone.
Because if we talk about it
But yeah,
in an objectively
yeah. So if you
bad
just
sense,
look up his
or
name
functional
in resources, so like I'll just show you.
the idea is
So if
we
you
want to
just do
optimize
from
happiness and that part of the
and
product of
Travis,
people
not president,
expressed like that is
you'll
a-
see
that
quite a bit of
raises
stuff
art
that he's
is a product that
posted.
raises
We
people
can
out
also
of
put like
suffering,
has link.
You know, okay. And that's
So
that's one
these are
thing,
some of the
you know?
papers that he has
or if we want to talk
shown.
about
So
it as
here's a
It's
few.
4 o'clock.
Thank you.
more, like, I suppose, like
There's a few that he's made. This is also a paper
thought
that
of as just a fact of life.
this is a
You
paper
know,
that he's done. But yeah, you can go through here and see a lot.
Thank you so much.
Yeah.
Because like
Yeah,
the
yeah,
implications of having
Do you want to take a photo of that so you know how to do it?
the implications of having to teach a machine how to think. Dude.
It's very interesting.
It gets anthropological, like
Yeah.
you have to define knowledge in some way.
Yeah.
So fucking cool.
The fact that he has like a link, oh not even a link, but just a formula to do it.
That's crazy.
Yeah, no, it's very interesting. Like he was explaining it to me last week. He was in town. It's really annoying. Like he like one day he's like, oh yeah, I'm sick going to a wedding. I'm like, oh yeah, where are you at? Are you at home with parents or are you abroad? He's like, oh yeah, I'm home with parents. I'm like, why didn't you just tell me to like sign the meeting like that last week instead of this week? It's like, whatever.
Who goes under the name of Bubbles?
Oh, that's Zachary.
And endure
Don't worry about that. Either way, yeah, but he was like trying to explain to me, like, yeah, I'm just trying to figure out how can I, because in order to figure out how smart something is, you have to figure out how stupid it is.
Yeah.
And so he's trying to define effectively stupidity. So effectively, he defined his intelligence as how, given how much information something is given, how much creativity does it have? And when I say creativity, if I teach you mathematics, can you sew a shirt? Technically, if someone gets taught mathematics, they're not necessarily taught. Yeah, exactly. But if they do know how to sew a shirt from giving other information, it's a very broad example. But if they're given some information and then they can then apply it to something else, that's creativity. And that's what he's trying to
find that
find.
information, but just like having the perception of how things work, like.
I'm more interested in the mechanics.
Yeah,
of
how's
what's
the
going on.
machine going for Travis, by the
For me
way?
today is the
Because he said that, because Travis is gone.
it's meta knowledge. How do you define like
Yeah.
how do you show a machine a concept like time?
I guess
So
I would
crazy.
like.
Yeah, how do you,
Or
like even the concepts, like, I don't know. You know,
Yeah,
it's,
that's right. Like
but it gets,
concepts. That's so fucking
it's cool, it's interesting. For me, it's like, that's so far into the weeds as far as the conversation goes. We have so far to go before we even start to tackle that stuff. I
yeah.
feel.
Like I know too. Like there's so much to figure out there. I really love it. How are you doing?
Doing good. Well, from my understanding, now that we didn't really go into it, all that we're really doing is
Alright, I gotta
like
tear down.
statistical analysis so far. That's what machine learning is. It's self-reinforcing statistical analysis, more or less. Whereas what it boils down to, right, is you're giving it a bunch of data and you're saying, hey, is this within variance of that data?
I know the NISPER project is something. From what I know.
I saw you checking if what was in range of the camera.
I realized that it's like, wait a second, I don't see. I didn't realize that the room, I almost said the class, the room is up there being streamed, and then I realized it's like, wait, I'm not in shot. And it's like, hold on. And then I saw the open table, and I'm like, oh, that must be the table, and I stuck my hand out, I didn't see it. It took me a second to realize that the first row was completely cut off.
Yeah, I mean, I tried, but this, you can only get a small camera with such wide angle.
I
mean,
think
that
this
works
is
for me,
mine
but
and
it's
this is
eugenics,
mine. What else could be mine?
I think these two.
Just this wire, this, this charger,
These three are the things I brought for me.
and this mini cell. Okay, if anything that you find is not yours, let me know.
Yeah, we'll
In
do.
case you forget.
But yeah, definitely ask Travis if you're trying to like implement anything machine learning. He's pretty responsive on Discord.
Guys, it's not necessarily joining. This is like
Yeah.
I really wanna format it with the implications and all of that.
Okay.
So I'm gonna try to get some reading done.
All right. Well,